Hello, can the people in Zoom hear me? Hello? There's only one person in Zoom. Hello? Can you say something? Oh, yeah, very good. Superb. Hello? Okay, so can the people in Zoom hear me? Can the people in Zoom hear me? All right, great. So today we are going to continue our discussion of section 4.3. So section 4.3 is on conditional variance and conditional expectation. So last time we talked about conditional expectation, which is this object. Actually, there are two versions of conditional expectations. One, conditional expectation of a certain random variable given an event. All right, so that is one version of conditional expectation. When one says conditional expectation, one is ambiguous. All right, unless you talk about conditioning a random variable on a particular event or a random variable. So in the simpler case of talking about conditional expectation of a random variable given an event, well, we are basically just using these formulas. That is, we are averaging with respect to the conditional PDFs and the conditional PMFs. So this is the conditional, what is this? PMF. And that is the conditional PDF. So we have talked about how to compute this, and I will not belabor the point and talk about this. So let us move on. The more difficult notion is the conditional expectation of a random variable given another random variable. So this is a very difficult thing. The first time I learned this, I couldn't learn this. So it took me many years to appreciate this. So I don't expect you to appreciate this even after this class, but we tried. So the notion of the conditional expectation of a random variable given another random variable is a random variable that takes on the value given by this whenever y is equal to y. So in other words, in a formula way that is very difficult to understand, so we'll provide examples later on. If I let z be this particular random variable, and this particular random variable, the conditional expectation of a random variable given another random variable, is a function of what you condition on, g of y. That is the certain function. But a function of a random variable is a random variable, as we have learned before. And it's given by a certain formula that I will use examples to illustrate. But actually, I've done so last time, so I will not belabor the point. The most important thing you need to know from the first half of section 4.3 is the law of iterated expectations, which is this formula. But knowing the formula itself is useless. You need to know how to use it. All right. So last time we have seen a few examples to use it. So we will continue those examples this time. So if you forgot the examples, you are lost. All right. So you need to recap the examples, because I'm going to talk about the notion of conditional variance, which is the second half of section 4.3. All right. So those are everything that we want to recap. So the notion of the conditional variance is the following. So we are going to introduce another random variable. And this random variable is given this symbol, variance of x given y. Okay, what is this? Well, this is a random variable that is another function of y. So whenever we condition on a random variable, it is a function of this thing here. Okay, but more precisely, it is given the formula variance of x given y, defined to be expectation value of x minus the conditional expectation quantity squared condition on y. So the conditional variance of a random variable given another random variable is like a conditional expectation, except there is a special conditional expectation. Now, notice the simple fact here. If y is absent, that means it is not present, right? Then this reduces or degenerates or particularizes to the normal variance. Because if you use your finger to cover this, and cover this, that means you're not conditioning on no one, all right? Then we have expectation value of x minus expectation value of x quantity squared, which is the vanilla definition of variance. Okay, so the notion of conditional variance, this is known as the conditional variance. Okay, introduce another random variable. This is known as the conditional variance. Okay. All right, this is being very disorganized, but the conditional variance is basically this notation here. And I'll illustrate this, how to use this notion shortly. So we just want to remark that the conditional variance, which is this object here, is a function of what we are conditioning on. Very important. It's just like the conditional expectation. This is a function of y. Okay. So, and it takes on just like the notion of the conditional expectation. It takes on the value given by variance of x given y equals to y whenever y takes on the value y. Okay, and what is this notion of variance of x given y equals to y? Completely analogous to the expectation setting. Okay, so that is nothing but the sum over x of x minus the expectation value of x given y equals to y, quantity squared, you average with respect to the conditional PMF. Okay, so now, as you know, we all do not like too many formulas, so we need to give an example here. Okay, this example is not in the book, it's nowhere. All right, so you either copy it or you remember it. Okay, so, or you can just look at my handwritten notes later on. Okay, so we have this simple probability table. Okay, when we have two random variables, x and y. And y can take on two values, x can take on two values. And so here x is 0, 0, 1. And this PMF looks like this: 1 over 5, 2 over 5, 1 over 15. And how much here? Okay, 3/5 plus, so 3/5 is how much? Over 15. 3/5, 9, 10, 1, 5 over 15, which is 1/3 here. Okay, let's just write 5 over 15. All right, so how do we compute the conditional variance? Okay, given y equals to y. Now, how many y's are there available to us? There are only two y's, y equals to 0, y equals to 1. All right, so say I'm interested in conditioning on y equals to 0. So now what do we do? We focus our attention, we focus our attention on this segment here, because this is the segment, actually it's called the section, all right? It's called a section, the y section. This section y equals to 0, So we are living in that universe. Now, when we are living in that universe, we are looking at the distribution of x. How is x distributed? All right. Now, x given y when y is fixed to be 0. Okay. Now, x can take on two values. X is equal to 0, x equal to 1. So now look at these two numbers here. We are living in that universe. Okay. So what is this number here? Very good. 1/3. And of course, this is 2/3. All right. So now what is the conditional expectation of x given y equals to 0? Now, expectation means this one times this one plus this one times this one. Can anyone do this in your head? Very good. Thank you, David. All right. So we can plug all these into the formula. So the variance of x condition y equals to 0 is equal to, well, here x runs over two values only, this value and that value. So we have 0 minus, what is the conditional expectation? 2/3 quantity squared. And we need to multiply this by 1/3 plus 1 minus 2/3. Hopefully I'm right. Multiplied by 2/3. And this is whatever it is. And I didn't bother to calculate this. All right. So it is whatever it is. This is the way to calculate the conditional variance condition on a particular event. And the event is that the random variable y takes on a certain number, little y. Okay, so this is just to recap how we deal with such probability tables. Okay, now you can go home to figure out what is the conditional variance of y equals to conditional y equals to 1. That means we focus our attention on this column here, and I will not do that. Okay, any questions? Sean, why are you not here today? Sean, can you hear me? On Zoom, all right, okay. I thought you always like to show up. Okay, so just as we have the law of iterated expectation, which is here, very important. There are not many things in life you have to commit to memory, but this one you have to commit to memory forever, because no matter whether you want to become an electrical engineer or an insurance agent, you need to use this. You know, you average, just last time I used the analogy, right? You want to calculate the average of the quiz scores across this entire class. You first calculate the quiz scores of tutorial 1. Then you calculate the quiz scores of tutorial 2. You calculate the quiz scores of tutorial 3. Then you do a weighted average. That is the effect of, that is the application of this special formula. I talked about it last time, so go and review the video if you do not know what I'm talking about. Okay, so whenever we have something to do with conditional expectation, you would expect that we will have something to do with conditional variance as well, right? So here is the next result, which is the essence of the second half of section 4.3, law of total variance. Now, there are many things in this class that you will find difficult. I know. But this is the thing that you will find the most difficult. Because this is the thing that I found the most difficult when I was learning probability, okay, from this book. So it says the following. Now, I'm interested to calculate the variance of x. So this is the variance of the scores of the quizzes of the whole class, quiz 1, all right? So the claim is that this is equal to two parts. The expectation of this new random variable that I defined just now, plus the variance of the conditional expectation. Oh, wow. Okay. Now, this is a random variable that we described last time, and I recapped to you this time. This is a random variable that I just described to you, and we did a partial calculation here. Okay. So, okay. So this is very mysterious, right? Extremely mysterious, especially to me. Why are there two terms here? Okay. Now, if you don't believe me, at least you can believe the mathematics. How can we get the variance of x? Now, I don't expect you to know what is the meaning of a proof in this class. I will never ask you to do a proof. So I won't use the word proof. I will use the word justification so that it is not so scary. So what is the variance of x? Well, you know, the variance of x is the second moment minus the first moment, quantity squared, okay? As I said, there are not many formulas you have to internalize. This is one formula you have to internalize. Now, this is a formula that was derived based on the standard definition of variance. But after a little bit of algebra, we can get here. Now, the justification starts from here. We are going to show indeed how we get this. And then I'm going to show you an illustration of why this is what it is. And then we are going to do many examples. Okay, so that is the agenda. So we are going to tackle this in two parts. First part, which is the second moment. Now, the second moment can be expressed by using the law of iterated expectations as the following. Now, the law of iterated expectations, you can put in any random variable you want here. You can put in the random variable Oliver. So this is x squared. Any random variable you can put inside. Okay. All right. So the law of total expectation or iterated expectations works as it is. Whatever you want to put in. So I now put in x squared. Cool. But do you remember what is the second moment? The second moment is the variance of x given y plus the first moment quantity squared. Where does this come from? This seems to be, I plucked it from the sky, okay? But the second moment, okay, is nothing but the variance. Is this plus or minus? This is plus. The first moment or the expectation quantity squared. Where does this come from? Did I pluck this from the sky? This one here? No, we didn't pluck this from the sky. We basically subtracted, or do we add? All right, we added the first moment quantity squared on both sides. You move this over to this side. Then you will get this. So now we basically condition on y throughout here, and we basically apply this green formula. So this green formula is being applied here by looking at every random variable y and, sorry, say wrongly, looking at every random variable x. So there are many instances here, and then we condition on y everywhere. Then we get that this second moment is variance plus first moment quantity squared. All right, so we have dealt with the first term here. Okay, no, where are we? We have dealt with the first term here. Okay, so this term here, maybe this is, let's say, term number 1. And then this term number 2. The term number 2, very easy. Okay, the term number 2 consists of expectation quantity squared. But by the law of iterated expectations, this is expectation value of x given y, take and further average over y squared. Okay, so now we have expressed everything in a very nice way. So now what remains is to put everything together. So variance of x is equal to the second moment minus the first moment quantity squared. All right, and now we are basically going to copy what we painstakingly derived here. Okay, so we're going to put this here. So this is the first part. This comes from the first part. This is the first part, part 1. And let me make this a little bit nicer. Okay, then we have the second part, which comes from this part here. Okay, so this is the justification. If you don't know the justification, it's okay. But now at this point, we have the usual stuff. I'm not going to do anything fancy here, but now we can give this a name, right? If you're very scared of this, we can give this a name GY. So we have that, we have expectation value of GY squared minus the expectation value of, well, this thing here is exactly GY. All right, so we have expectation value of GY quantity squared. And what is this thing here? What are these red things here? Very good, exactly. That is exactly the variance. So we have this first term here, which we are going to keep untouched. And we have the expectation of GY squared minus expectation of GY quantity squared. So this becomes variance of GY. But what is GY? I'm going to skip step here. GY is the conditional expectation. And this justifies the whole thing. All right, because here we want to try to justify the law of total variance. And the law of total variance says expectation of the variance, expectation of the conditional variance, plus variance of the conditional expectation. Okay, so this is the justification. Whether you know this or not is not so important. But if I don't show this to you, I'm not doing my job. So I have to show this to you. But what I need you to know is how to use this. But before we know how to use this, we have to be convinced that I'm not making a mistake in these calculations. And this calculation is actually believable. The result is actually believable. So we are going to have an interpretation of this result. Pictorial interpretation, pictorial proof, or pictorial justification. Any questions on this justification at the beginning now? Feel free to ask any questions on the justification. Let me go through the justification one more time. What are we trying to justify? We are trying to justify this thing that you should internalize. As I said, not many things you should internalize, but the law of total expectation, law of total variance, you must internalize. Okay? So where do we start? We start with what we know. The variance is these two parts. Second moment minus the first moment quantity squared. So we are going to deal with this part here, which is a little bit more difficult. So by the law of iterated expectations, as long as we keep one of the terms here invariant, that means don't change this. If this is Oliver, this is also Oliver. Okay. Then we have that this is the second moment is the variance plus the first moment quantity squared. And we can now apply this to the fact that everybody is conditioned on Y. If you don't carry the conditioning around, you are wrong. All right. So basically, now we need to carry the conditioning around, carry this, carry this, carry this. All right. Then the second term here, number 2, is the vanilla. That means the standard law of iterated expectation. So we just keep the square, bookkeeping this properly, and everything inside is just a law of iterated expectations. Then the rest is algebra, careful bookkeeping algebra. If you are very scared of this, you can give this a name, call it GY, or you can call it Z. And then you notice by the standard definition of variance, this is the variance of the random variable GY. Okay? Because the variance of a certain random variable is the second moment minus the first moment quantity squared. All right, so this is the justification, and I went through it one more time. All right. Before I talk about examples, which will consume a lot of this class, let us interpret the result. Okay, what is the interpretation? Now, suppose my random variables X and Y are spread out in this particular way. This is very ugly. Okay, my random variables are spread out in this particular way. Okay, they consume this amount of area. Now, when Y is very big, X is very thin. When Y is moderate, X is spread out a lot. Okay, when Y is very small here, then X is also spread out not too much. More precisely, okay, let me take 3 representative values of Y: Y1, Y2, and Y3. And what is the conditional density or conditional PDF when I condition it on different values of Y? So the PDF will be like this. Okay, those are the mini PDFs, conditional PDFs. Okay, so now we are interested in the variance of, variance of X. Okay, we are interested in the variance of X, and we are interested to try to understand this particular formula here. The variance of X is this particular formula. Okay, can we understand what these terms mean? Okay, variance of X equals to this. Now, so as I already mentioned, this is the conditional density of X given Y, X given Y3. This is the conditional density X given Y, X given Y2. This is the conditional density X given Y, X given Y1. As you know, when we condition, we are living in that universe. That means we are restricting ourselves to this. We know because Oliver told us that Y is Y3. So we are living in this world. And so we are our belief about X is restricted to this little graph here. Now, if I drawn this all properly, right, then all these conditional means would line up. And this would be our expectation of all X given Y is equal to Yi, I running from 1 to 3. So there's no variation here. So all the conditional expectations of X given Y equals to Y, be it 1, 2, or 3, or anywhere in between, they all seem to line up. So this one seems to be 0. There's no variation here. So the only variation that comes about when we determine the value of X is in fact coming from, where is it coming from? Here, the individual variations of the densities. So here we have the variance of x given y equals to y3. Here, that is the variance, basically the spread. In the middle, there's a lot of spread. At the side, there is not so much spread. Here, less spread. Okay, variance of x given y equals to y1. So all the contribution comes about because of the spread of x given y. Okay, the blue part. In this particular formula, okay, let me put a remark in English. The variance of x comes about only from the variances, the individual variances, variance of x given y equals to y for all y. Okay, so that's where it comes from. So it seems like, hey, gee, it seems like this term is redundant, right? Why do we have to have this term? All right, because it seems that the variance of x is just going to be an average of the variances of x given y equals to y. All right, I'm just averaging across the different variances. But no, it is because I drew this picture in this particular way, and all the variances of x given y equals to y line up. If I drew it in another way, by the way, before I continue, any questions here? Yes? No. The expectation of x, okay. The expectation, okay, good point. What we can see here is that no matter what y you choose, no matter what little y you choose, this is all the same. At least from the way I drew it, all line up. It's meant to be a vertical straight line. Okay, so what we can say is that actually the expectation of x given y equals to y does not depend on little y. However, the variance of x given y equals to y does depend on little y. Here, the spread is bigger. Here, the spread is smaller, although my picture is not very good. But you can see here the spread, okay, if I drew it here extreme, right, the spread is very small. It's only a small little hump. Here, the small, very small. So, however, the variance of x given y equals to y does depend on little y. That's the point. I think, David, does this answer your question? Thank you. Yeah. So here it seems like I have just lost one term and the law of total variance seems to be too complicated. No, everything is required if we draw a more involved picture. All right. So the next picture I will try to draw in a better manner. We'll try our best. This is x, this is y, and we are going to draw this skewed picture. Okay, this is meant to be skewed. All right. So now, as usual, we are going to fix three y's: y1, small, medium, large. Okay. Now, maybe we make this really small. Then you can see something. So when I'm y equals to y1, I'm living in that universe. So I have this conditional density. This is not in the book. Okay. Then here I have another conditional density. It seems that the spread is bigger. Okay. And here we have another conditional density. Okay. Well, this is meant to be straight. Okay. So as you can see here, each one of these guys here has a certain variance of x given y equals to y. This has a certain variance. Variance is the spread. Okay. Y equals to y2. And here we have a different variance, y, x given, y3. But the way I drew this is such that there is more interesting stuff because here the conditional expectations are not the same. Y equals to y1. Here you have a different conditional expectation. Expectation value of x given y equals to y2. And this color I know is not very good. We'll try our best. Okay, and this is expectation of x given y equals to y3, and so on. So here there is a spread in terms of the variances condition on each little y, And there's also a spread of the expectations, okay? So now the punchline is the variance of X now has two contributions, okay? Number one, which is what we saw last time, variance of X given Y equals to Y for different Y. We need to take the expectation across different Ys. And number two, so this one here, this first term here, all right, comes about because we have different variances for different Y. Here the spread, what I'm coloring now, is bigger. Here the spread smaller. So we need to average out. This comes from, this is the green part. Next part here is, what is this? Expectation of X given Y equals to Y for different Y. Okay, take the variance of this random variable, of the random variable associated, the random variable expectation value of X given all possible values of Y. And this comes about from this particular angle here. Okay, this is very ugly color, so let's use a different color. Okay, maybe this one. Okay, this color here, this comes out because of the spread. Now the expectations are also spread out. Just now it was fixed. So the variance of X has exactly these two contributions, different variances for each different Y and different expectations also for different Y. So we need to now average out the variances, these three terms here, and actually there are many, many terms, okay, but I can only draw three. And we need to consider the variability or the spread of the expectations as well. So in the simple case, when all the expectations line up, then there's nothing to calculate here because the variance of this part is 0. But when there's a spread here, well, then there's something to calculate. You need to take the variance, okay? So that is a pictorial proof or pictorial justification of the law of total variance, which is something that you probably are very bemused by because there are a lot of things happening here. Expectation value of the variance, variance of the expectation. All right, you need time to digest this. I cannot say that you will absorb it straight away because I didn't. Okay, so any questions on this picture here? This picture here. This is a picture that illustrates the law of total variance. By the way, I'm not so smart to come up with this picture. This picture I got from Stack Exchange. Okay, this is not in the book. All right. Any questions? So I don't need you to know how to justify this formula. I need you to know how to use it. I don't need you to draw such a nice picture either, but I need to do my job to explain to you what are the components, where all the components come from, and how it's justified. Okay. So in the remaining 25 minutes, we will do some examples to illustrate all these points. Okay. To illustrate how to use the law of total variance. All right. So these examples we have seen from last time. And we will rehash these examples because last time we stopped our calculations at the expectation. Now we will proceed on to do variance. Okay. So we have now n independent tosses of a bias coin with bias. What is bias? Bias means the probability of heads, okay, or probability of tails, whatever, doesn't matter. Bias Y. Oh, very interesting. Now, your coin is not unbiased. Your coin is not 70% biased either. But before you start tossing the coin, right? Someone, say Valencia, all right? She generated a random number from Python between 0 and 1. And she said, this is the bias of the coin. And indeed, this is the bias of the coin. And we're going to toss it n times. And we're going to say something about the n tosses. Okay? So one more time. All right? we have a certain coin. This is meant to be a circle. All right, we have a certain coin, and the probability of heads is a random variable y. The probability of heads is a particular random variable. There are two layers of randomness now. The first layer of randomness is, what is the bias of the coin? The bias of the coin is a random variable, and it is a random variable drawn uniformly from 0, 1. Okay, so this makes sense because the bias must be a probability, must be between 0 and 1. So before the whole experiment started, okay, Valencia generated a random number, this one. Okay, now we fix this number, and then we are going to toss the coin. So there are two layers of randomness. One is y, and another is the n tosses. Okay, all right. So the bias of the coin could be anything from 0 to 1, not necessarily 0.7. Okay, but it is something. Okay, so last time we saw the following: x. What is the expected value of x given y equals to y? Or what is x? X is the, I didn't say this. Okay. So x equals to the number of heads in n tosses of the very strangely biased coin. Okay, let us try to recap. What is the expectation given that the bias is little y? Okay, little y very difficult. So let's say 0.7. Suppose the bias is 0.7. How many tosses do I expect to have in n tosses? John. The bias is 70%. What's the number of heads I expect to get? So this is, okay, so someone help you, right, John? So next time you will answer the more difficult question. This is the simplest question. So more generally, this is ny, okay? All right, so next time we will have John answer the more challenging question on variance, okay? So we have the expectation of x given random variable y is ny, like this. So notice that this morphed from the lowercase to the uppercase because we are now conditioning on a different object, a random variable. So what we have is, okay, before that, what is the variance of x given y equals to little y? Now this is a Bernoulli random variable. Remember there's a Bernoulli. Bernoulli means a 1-0 random variable. Okay, now John, what is the, wait, this is a bit difficult, okay? X is the number of heads in n tosses. Okay, say one toss only, one toss, n is 1. What is the variance of the outcome? Suppose y is 0.2. Anyone can help John. We saved the most difficult question for John. This is intermediate. Say 0.2. Yes, and where did that come from? Y times 1 minus y. For the case n equals to 1. Y times 1 minus y. When this is 0.2, my internal calculator tells me that indeed this is 0.16. But suppose we have n tosses, independent tosses. Okay, now John, what do I have to append here? Is a function of n. Now, the tosses are independent. N choose 1, so complicated. Also can, n choose 1 is okay, but n choose 1 is n. I don't know how it came out with n choose 1. Because you have n independent tosses, so suppose you have a independent tosses of a fair coin, x1 sum up to xn, the variance of this, and all the people here are independent. That is just nothing but the sum of the variances. All the guys are independent. So basically, David answered me this part here. We just have to multiply by n. Okay, so very good. So now we have the variance, and so the variance condition on a random variable y, I just replace the little y by capital Y. Okay, right. So we prepare ourselves all these statistics. Now I'm interested to compute the variance of the number of heads that I have. This is very difficult. If you have not come across my lecture, you wouldn't know what to do. All right, because there are two sources of randomness. One source of randomness is the capital Y. One source of randomness is the capital X, which is the total number of heads. So we always adopt a, engineer people, right? Always have to adopt a divide and conquer strategy. We divide into the little y first, then we conquer the whole thing, all right? So we have already got all these things prepared. The law of total variance says, what do we say? Expectation of the variance of X given Y plus the variance of the expectation of X given Y. This is what we showed just now. So now we are going to compute each of these components, part 1 and part 2. So let's call this part 1. So now we have to plug the variance X given Y inside, right? So this is the variance Y. Okay, where does this come from? This comes from here, which we painstakingly calculated, and hopefully John fully understands the calculation here. Cool? So now, because expectation is linear, this becomes expectation value of Y minus expectation value of Y squared, linear. That means you can bring the n outside and then you can push the expectation operator as far in as you like. Okay, so there are a few things here that are difficult to calculate, but there are a few things here that are easy to calculate. And I will ask you how to calculate the easy things. All right, someone tell me what's expectation value of Y from this picture. Very good. Someone tell me how to calculate this one. Okay, from this picture. You can do integration. How did I calculate this? Okay, we can do integration, but we don't need to. Here's my shortcut. Okay, minus the second moment is the variance plus the first moment quantity squared. Okay, but I somehow, because I'm so experienced in this sort of things, I know that the variance of this guy here is 1/12. The variance of this guy here, I know is 1/12 because I memorized this. But I don't expect you to memorize this. You can do integration, okay? And I'll show you how to integrate this. 1/12 plus 1/2 quantity squared. You need to put the brackets properly. And after you are said and done, this is n/6. All right. Now, what is a more how to say primitive way of calculating this? So expectation value of Y squared, you can just do integral this one fyy, which is equal to 1 dy from 0 to 1. Okay, so this one will give you 1/3. I look at it, I know it's 1/3. Okay, and this one is 1/4 plus 1/12, which is 1/3, which is okay. Sure, correct. So now we have tackled, what have we tackled? We have tackled the first part. Oh my gosh, wrong color. Okay, so we have tackled the first part here. This is part 1. The next thing is we have to tackle the second part. Okay, it's not very difficult. Okay, so now any questions on the first part? Okay, so there are two different ways of computing the second moment. You can do the integration way or you can do the shortcut way. This is the integration way. This is also 1/3. So 1/2 minus 1/3 is 1/6, which is correct. All right. Any questions here? So this is a bona fide random variable, and it comes from here. I just plug this inside here. Okay. Let me get rid of all this. Maybe I can put this on here. 1/3. Okay. So now we need to tackle the second part. All right. The second part. Okay. Are there any questions on the first part, which is this part 1 calculation? If not, we can go to the second part. Variance of the expectation value of X given Y. Now that is variance. Okay. Well, this is n times Y. Right? Where did this come from? I didn't pull it out from the thin air. This comes from here. Oh, maybe not. It comes from here. Here. You see? All right. We're just plugging the definition of expected value of X given Y random variable inside here. So we just bring it down here. So now, variance of NY. Who can tell me how to simplify this? Let me ask. I know there are 2 Samuel, so let's toss a coin. Samuel. With equal probability, either one can answer. How can I simplify this? How can I get a handle on this? Okay, variance of 7x, maybe 7z is what? Very good, 7 squared. At least you understand. Okay, so n, okay, you have n squared variance of y. We have already calculated variance of y just now. Actually, it's n squared over 12. Because for a uniform random variable, this number 12 always appears. Variance of y, we have computed it. Okay, or you can go and painstakingly compute it. Okay, but I'm not going to do that. So now we can put everything together. So this part here comes from, I'm running out of colors already. Okay, this part here comes from this part here. So we are going to amalgamate these two parts. We're going to combine them together. Here we have this, okay, n over 6 plus n squared over 12. Is this correct? Okay. So as you can see here, this is actually not very easy. Okay. If I give this in an exam, I'm sure at least 1/3 of people will trip up. Okay, I'm sure, because I know that I will trip up also to get all these constants correct. But what I know I won't trip up is I know how to apply the formula. So all the numbers are not so important. More importantly, how you apply the formula and whether you know what to do. Okay, so that one I can assess even if all your numbers, not all your numbers are correct. Any questions on this calculation? So last time we just did the expectation value of x, okay? Which expectation value of x, remember, you will basically compute this, and this is by the law of iterated expectations, the expectation value of x. So you just have to take expectation value of y here multiplied by n, not very difficult. But the variance is much more difficult. If I tell you at the beginning, can you guess this number? No, cannot, all right? I cannot. Okay. So this is, and any questions? This is an application of the law of total variance to this particular example. Any questions? Sean, any questions? Yes. Oh, this is a formula. All right, it always holds that. Okay, here proof. Variance of 7z is 49 variance of z. Always. Proof. How to prove this? So this is equal to expectation value. Okay, this is a fact of life, okay? There are not many facts you have to remember, but this you have to remember. This color is very ugly, so let's use a different color. Expectation value of, you put the random variable here, minus the expectation value of the random variable, quantity, what is the definition? Quantity squared, like this. Okay, instead of doing 7, right, let's do A squared here. A, okay? Now, but you notice that you can bring out A squared here, Z minus expectation value of Z all squared. So this becomes A squared expectation value of, Z minus expectation value of Z all squared. So this becomes A squared variance of Z as desired. All right, so David, there are not many things in life you have to remember. This is one thing. Okay. How do I calculate the variance of y? How to calculate the variance of y? Because I remember. Okay, but if you don't know, you calculate the second moment first, which you can follow the integration there. Can? All right. So how do I calculate the variance of y? Okay, can, no problem. Variance of y for the uniform random variable. So y is uniform on 0, 1. You take the second moment minus the first moment, quantity squared. And the second moment by integration is 1/3. The first moment is halfway. Okay, first moment you can just eyeball. Eyeball means you look at it. All right, you look at it and then you place the wedge here and then it's all balanced. Halfway. All right, then this becomes 1/12. More generally, it's b minus a over 12. B minus a squared over 12. because I remember a lot of things from Wikipedia. Okay, so some things in Wikipedia are good to remember, some things you don't have to. All right, I remember a lot of distribution properties from Wikipedia. So yeah, you may find it a bit fast, but if you are uncomfortable, you can go back to the definition of the variance, and then you compute the second moment and you compute the first moment quantity squared here, and then you get a number, and then you see that indeed I'm not lying to you, that variance of y is 1/12 as desired. Okay. All right. So in the remaining 12 minutes, we will do one more example. Okay, but if you ever teach this type of class, right, you should not do what I do now and squeeze in a difficult example in the last 12 minutes. All right, but here I'm going to violate my own rule and I'm going to squeeze in one difficult example in the last 12 minutes because you have seen this example before. This is called example 2. We are going to break a stick of length L. Actually, this is the third time you see this example. L into two parts. In two parts. Actually, in two parts first. Then we are going to break the stick into another two parts later. So now this is a stick of length L. And then we are going to break it. And then we are going to call the remaining length random variable y. And the way we break the stick is uniformly at random. So uniform around this. So suppose, okay, Liao Xue broke the stick and she got this, which is a random length. Okay. Now, Liao Xue gave this stick to Sean, who is not here. So he virtually break the stick and he got, oh, a very short length, maybe like this. Okay, so Sean took the stick from Liao Xue and then he obtained x, which is a random variable uniformly distributed between 0 and capital Y. So we want to understand now, what is the variance of x? Very difficult, right? Why is it so difficult? It is because the intermediate object is random. The intermediate object is random. If we are to compute the variance of y, very easy. It's uniformly distributed between 0 and little l, which is deterministic, non-random. But now this one has two layers of randomness here. Okay. Now you can imagine, okay, by common sense, which I think a lot of people have, that the expectation value of x will be L over 4. Common sense. And we proved this last time. But by common sense, you cannot guess what is the variance of x. Because it's a strange number that we are going to produce in 7 minutes of calculation. Yes, David. Law of total variance. Yes, that's half our strategy. Half our strategy. Thank you very much. What is the other half? David outlined half the strategy. What is the other half? He said, oh, we know the variance of y given x, or we know the variance of x given y, or blah, 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 all right? But we also need to know the expectation, because as I mentioned, here there are two components. Just now, David outlined one of the components, either this or that, but he didn't tell the whole story. So now we are going to do the whole story. David, understand? Okay, so now we're going to collect the statistics. So before that, y is uniform on 0L, which means that the density looks like this. 1 over L FYY. Okay, so we're going to collect the statistics, all right? So variance of x given y equals to little y. Okay, so this is one important parameter. So what is this? Oh, I said at the beginning that Liao Xue broke the stick, right? So this is the stick that was remaining from her breaking, and she passed over to Sean. So what is the variance of Sean's breaking? So we already know that Liao Xue already broke the stick to be little y. Her stick was little y. And then now this is uniformly distributed from 0 to little y. Okay, so this must be y squared over 12. Okay, because we are uniform. And I said just now, b minus a squared over 12. Okay, so when we condition on a random variable y, then we change the little y to capital Y like this. Okay, that's all. Right? So when we want to compute the variance of x, there are two components. Variance of x is equal to, by the law of total variance, x given y plus expectation, variance of expectation of x given y, like this. Very good. So now we have done the work of this one. We're going to put it inside here. So this is number one, expectation value of the variance of x given y. So what is this? Now we just have to plug it y squared over 12 inside. Okay, this one is okay. So we can just use the same old formula of how to compute the expectation of some function of y. So we integrate from 0 to L of this one times 1 over L, the density. So here I'm going too fast. This is the density of y. And then this is the y squared, and then you need to put dy here. Now, if I integrate this by my head, all right, very fast, then what do I get? I get L squared over 36. I can see this. Yeah, because you have cube and then divide by one thing. Okay, but this is mechanical. I'm not going to teach you how to integrate things. Okay, you accept this or you do it slowly. You cannot do it, you ask me. All right. So we have the first component. We have the first component here. So now we are left with the second component, which is arguably easier. So variance of the expectation value of x given y. Okay, so we collected some statistics here, right? All right, one thing we didn't collect and we probably should collect first is expectation of x given y equals to little y. Someone can tell me this. Okay, we get. So if Liao Xue broke the stick, right, and the stick is little y, what is the expectation value of Sean's breaking, which is x? What is this number here? X is uniformly distributed from 0 to little y. This is uniform from the model last time, uniform. So where are we most likely? Y over 2, thank you very much. So we have expectation value of x given capital Y is y over 2. So we all just have to plug y over 2 inside here. Okay, so what are we going to do now? All right, David, what are we going to do now? We have this factor here. Okay, thank you very much. We will ask David to answer the more difficult question. Variance of y here. Okay, what is variance of y? Y is this object here. I eyeball it, I will know what's the variance of y. It has something to do with 12. It is L squared 1 over 4 times L squared over 12. L squared over 48, I believe. All right, so as I mentioned, the most difficult thing will be answered by David because some people help. So what do we now do to compute the variance of x? What two numbers do we add up? The 2L squared. Perfect. Where does this come from? This does not drop from thin air. We proved it. It comes from here, right? We justified it as two components. And this is L squared over 36 plus L squared over 48. And I'm not very good with these things, but this is something that you cannot guess from the beginning because you need to do some calculation. All right, I think it's 7. So this is something you cannot guess from the beginning. You have to use the formula of law of total variance. Total because you have to average over y. But you need to average in an intelligent manner. The averaging involves taking the expectation of the random variable variance x given y. It involves taking the variance of the expectation. Where do these things come from? You have to remember this skewed picture. Okay, this skewed picture tells us, okay, you need to average the variance and consider the variance of the averages. Next time, I will tell you another story. Yes, David. Back here. Okay, what holds is that fact of life. If Z is a uniform, continuous uniform random variable on AB, then the variance of Z is B minus A quantity squared over 12. This is true. Okay, so now we have variance of Y, and Y is uniform 0 to L. So you take L minus 0, square it, divide by 12, you get this. Always true. You can go and check Wikipedia. But it's best you prove this on your own as exercise. David, are you half convinced? I know what you are confused by. I know precisely what you're confused by. Because in the cheat sheet that we produce for you, we produce the continuous version and the discrete version. And in the discrete version, we have +2. You are looking at the wrong formula. Now very clear? Okay, this is continuous land. In the discrete land, I cannot really remember. If Z is uniform from integer A plus 1 all the way to B, then this is something that I cannot fully remember, but I think David has it right in front of him, so you can go and check with him. This one I don't remember, but there's something to do with +2 here. Okay? So, David, is this clear, this calculation? Okay, so we have to put into place two things. So every time we do this, we have to collect the statistics first. Collect this and then plug into the formula. That's the way to do it. Right, I will see you guys on Thursday for the tutorial and for the lecture. Thank you very much for your kind attention and active participation. If you have any questions, feel free to ask. If you don't have questions, do the tutorial, okay? See you. Sean, come for the tutorial. Should we stop this? I think we should stop this.